David Heavey, il direttore vendite di Inductotherm, con sede a Droitwich, mentre io sono Mario Cagliero della Lamca. Lui parlerà in inglese, ha fatto una serie di slide che però sono state tradotte e quindi voi le vedrete in italiano. Se ci sono domande o cose del genere, se volete parlare direttamente in inglese a lui non ci sono problemi, se no provvederò io a tradurle. Per qualsiasi cosa siamo qui a vostra disposizione.
Good morning, ladies and gentlemen. My name is David Heavey. I'm the Director of Sales for Inductotherm Group Europe. That means I'm Head of Sales for the whole of Europe. I'm standing today. John Steer would have done this talk, but unfortunately he's unavailable. So I will do my best. To introduce my company, Inductotherm Group Europe manufactures equipment for the European market. We're part of the worldwide European group and a specialist melting company. We manufacture now in 23 countries around the world and employ over 4,500 people. We have sales currently of $1.2 billion per year, and the bit I like is that we're a privately owned family company. I want to talk about just a slide. Okay.
Allora, l'italiano lo capisce, leggerlo lo mette un po' in crisi. Scusateci. Tra l'altro ha detto che nella sua presentazione che il responsabile per l'Italia in questo momento purtroppo non può essere presente, se no sarebbe stato lui a fare la presentazione e David seduto ad ascoltare.
I want to talk about the development of high power melting equipment and efficiency of operating induction for medium frequency induction furnaces. Medium frequency solid state power supplies for induction melting have been around in some form for nearly 50 years, and in usable form for melting in more than 40 years. So we're not talking new technology, we're talking developed technology. In the early days, ratings were available and power devices were low, and the clever electronic controls that we have today were still to be invented. The industry moved forward slowly, and in around about 1998, the power supplies reached around about 3,000 kilowatts, what we would consider quite small today. At this time, the De Globe foundry in Holland, now Componenta, were needing to re-equip and achieve levels of production. They were considering two power supplies of 3,500 kilowatts, each with two 410 furnaces. So 4 furnaces in total. However, they realised that this would require 2 crews of operators in a country where the cost of labour was very high. They suggested a better commercial solution for the foundry was 1 power unit of 7,000 kilowatts and 2 7.5 ton furnaces. This was at the time twice as big as any manufacturer had built at that time. They went ahead and the savings were tremendous. Half the personnel, half the maintenance, half the water systems, half the controls, less space was required and lower cost of installation for the same production as their original plan. This was a point in time that was the start of the high power revolution. Okay, and this is a picture of what it looked like in those days. I imagine it's a little dirtier today, but that's still running today. At this point, things moved quickly, and equipment went in Europe from 8,000 kilowatts to 9,000 kilowatts to 10,000 kilowatts, 12, and on to 15. And 15 is currently the largest, I believe, the largest that we've installed in Europe. And the most common configuration was a single power unit and 2 furnaces. This is a picture of what it basically looks like as a package. So that's 15,000 kilowatts of inverter power. Next one. And it's a typical foundry. It's an Italian foundry. These are 12-ton furnaces and 8,000 kilowatts. So where are we today? Today, induction melting furnaces are being built up to 25 megawatts and 50 tons furnace capacity. And there seems to be no upper limit. The largest we've built in Europe is 85 tons with a little less power than that. But today they're now replacing arc furnaces in steel mills up to these sizes without the higher levels of electrical supply system contamination, fume pollution, and at lower cost. So I want to do a little bit of revision here. I'm assuming you all understand induction, but I think it's always wise to just describe what is it. We supply an alternating current to a coil, which creates a magnetic field. That magnetic field induces a current in the magnetic charge, and secondary eddy currents then generate a heating effect directly in the charged material. Now, this is all very clever to have big advances in semiconductor power supplies, but induction furnace system comprises a power unit and a furnace. An induction furnace is fundamentally a copper coil wound around a refractory crucible. And when supplied with all this power, it will attempt to jump up and down at the frequency of the power supply. If the coil moves, the refractory is allowed to move. And as we all know, refractories like stable temperature and support to resist movement. Or they crack. Cracks allow metal ingress. Metal ingress reduces the refractory life, and downtime is increased. And therefore our view is that an important feature of an induction furnace is a rigid support substructure, and that becomes paramount. There are 2 main furnace design philosophies existing today. One is to support the coil, and the other is to allow the coil to float. The first requires a much more rigid structure, which impacts on the size, the weight of the structure, and of course the manufacturing cost. Inductotherm's view has always been that maintaining the coil and thereby the refractory and compression is best. Others will have other views. Inductotherm can point to foundries using the typical automotive configuration of 8,000 kilowatts and 12 tons with refractory lives in the order 350 to 500 melts. And I can take you to those foundries. So this is the Inductotherm approach. I'm not really going to discuss others, but we go for a steel shell, massive steel shell structure where the coil is clamped in compression both radially and longitudinally. The merits of the 2 types of designs that I touched on can be argued, but the fact remains that refractory does not like to move and expands with temperature. So there are some fixed issues there. Okay, limits to power, the practical approach.
They're a bit small. Hello?
There have been small furnace applications where 200 kilowatts has been applied to 40 kilos, and these have been used to give power ratios of 5,000 kilowatts per ton. And this would be used in an aerospace one-shot type of process. This is not practical for modern iron foundries because there are furnaces are part of a continuous system where raw materials have to be brought in and molten metal has to be taken away. So the rate of production must be matched. Today it's more common to select equipment on the basis of a furnace will melt in 40 to 45 minutes, leaving approximately 10 to 15 minutes for alloying, slagging, sampling, and have the furnace ready to pour in about 50 to 60 minutes. 45-minute melting times require 750 kilowatts per ton when melting iron. So the furnace is no longer the limit of the power, the production becomes the limit of the power. My opinion is that this works. Faster melting means the furnace operators can't keep up and it's difficult to charge the furnace. Slower melting and the operators are not fully occupied and productivity suffers, and we see this all the time. Another benefit of high power density is stirring versus the frequency. Good iron quality requires controlled carbon addition, and one of the main benefits of induction furnace is the magnetic stirring that is being created. All other things being equal, the stirring magnitude is inversely proportional to the frequency. So the lower the frequency, the more the stirring. However, stirring is also affected by power density and the furnace geometry, and in this way, high power furnaces can increase productivity. By way of example, the old style 50 Hz furnace with 12 tons would typically have had up to 2.5 megawatts of power on it, while similar stirring from a medium frequency furnace would be between 8 and 9,000 kilowatts. By graphic, this is 8,000 kilowatts and 12 tons. And the points of the areas of interest here are the meniscus height and the metal velocity turbulent factor. These are nice, but they're difficult to relate furnace to furnace. So if we compare 8,000 kilowatts and 12 tons at 200 Hertz, and for 2,500 kilowatts, 12 tons and 50 Hertz, we see that the meniscus is much lower for the lower frequency furnace, but that the stirring velocity is very similar. So restrictions. There's no real theoretical limit to how much power you can put on an induction furnace. The restrictions are all external. They are the strength of the furnace structure, the charging capability, the batch size that the business requires, the metal flow out to the moulding lines, operator capability. Operator capability is a big issue. The metallurgy and excess metal movement, refractory life, and the ability to get the power in by matching the changing load of the charge conditions. Control the furnace. It's no use having all this power available if we cannot transfer it to the metal charge in a batch melting process. And this means that the inverter must be able to control to match the changing electrical characteristics of the charge. It's vital during the early part of the melt that the metal charge is, when the metal charge is cold and highly resistive. At this point, the subject, we could have a paper all on its own, but I think all the manufacturers would agree that ignoring their own products, the best scientific, technical solution is a voltage-fed series inverter. I'm sure that will raise a question. So, to talk about the benefits of high-power furnaces. Fast, flexible melting and operation of the furnaces, reduced number of furnaces and reduced holding requirement, reduced steady state losses and best energy. Reduced labour costs over multiple furnace operations, rapid alloy changes, less slag, less metal loss, batch melting efficiency, and induction furnaces are now even replacing arc furnaces in the steel mills. So that was a little talk about how we got there, why high power furnaces are a good thing. I want to talk a little bit now about managing the melting efficiency. We can argue about the numbers, but my feeling is that about 50% of the energy used in a foundry is used in induction melting. And because of what I told you earlier about efficiencies reaching their early heights, the furnace equipment manufacturer will not be able to help with your energy efficiency. And if we look at the development over the years, we go back into the 60s, power units were in the low 80s. Today, power supply efficiency has reached, conversion efficiency has reached 98%. This is unlikely to increase significantly in the future. It's just kind of we're at the line. So where does the energy go? There's the heat content of the metal. The gods fix that. We have no influence. Which is here. The power unit will have some conversion losses, transmission of bus bars, thermal dissipation is quite high. I squared our losses in the coil will be in these kind of numbers. Shunts, cooling coils. So if we start out with the metal needing this much energy, it's always going to use about that much energy to melt. Assuming it's iron, it's 1480, and that's the... Now I took this number out of a paper of a very prominent competitor, so I know I'm not cheating. So control of the melt. Melt metal, not non-metals. Use good quality, clean metallic charged materials. Non-metallic materials can have heat contents many times higher than the metal. And if I give you a kind of an example, if we assume a 10-ton furnace with 500 kilos of sand from the returns, that will represent at least 1,000 kilowatt hours for nothing. You will lose production time while you remove it as slag, and then you will pay again when you dump it in the ground. So don't put it in the furnace if it's not going to make castings, if you can possibly avoid it. Always melt from a cold charge. Never hold metal in the bottom of the furnace. Every melt, every time. Induction melting is more efficient when the metal is cold and highly resistive. And in addition to the circulating currents caused by resistance, contact heating, this will increase the melt rate. This here is the reason why the melting rates that you generally achieve are better than are claimed by manufacturers.
Ci dovrebbe essere un video, ma non funziona. Come è successo al collega prima, non siamo riusciti a farlo.
Show it at the end. If I can find it. Okay, batch melting versus heel melting. I said never leave metal in the furnace. The most pessimistic view you can have is that the efficiency loss is at least 7% between metal starting from molten and metal starting from cold. If we take an example of iron melting, then this can come to, in fact, more like 35 kilowatt hours per ton. That's every ton Every time you melt will just be wasted. Other things to do. Don't overcharge the furnace. I go into hundreds of foundries. Charge material that's up on top of the furnace. It feels like a good thing to do, but it loses efficiency in the furnace. Always feed the charge at the rate it's melting. Don't hold metal at temperature. And if you must, at least close the lid. Open furnace losses are many, many times the closed furnace. Fume extraction. We need to remove the fume. But the fume is high in the start of the melt and very low in the end of the melt. So control the fume to use less flow and pressure. Because all that happens is the air takes the energy away. Operational management. It's not just the operators, it's the chief as well. Plan the melting production to match the casting requirements. Don't just melt it and wait. If you don't need the metal, don't melt it. Never hold metal, it's just an extra cost. I agree you have to, but minimise it. When not charging, close the furnace lid. Radiant losses are very high. Empty the furnace as quickly as you can and restart melting. Sounds like common sense, and many of you will understand what I'm saying and know what I'm saying, but many melting operations ignore these basic facts. Okay, that's all I have to say. Thank you very much.